Alright, hey, today we are adding another piece to the puzzle to this discussion about weather. There's lots of different smaller ideas that we have to master and understand so we can have a really good conversation about what causes weather. And today we're talking about how the atmosphere is heated. The heating of Earth is really important to air pressure, and air pressure, if you remember, is really important to the formation of weather. So it's important we have some understanding of how our atmosphere is heated. And it might be a little different than you might think because Earth's atmosphere is actually heated from the surface of Earth upward to outer space. And it's not the other way around. A lot of people think, oh, the sunshine comes from outer space, so Earth is heated from the top down. And that's not it at all. Earth's surfaces absorb this solar radiation. And then Earth's surfaces, like the dirt and the buildings and the parking lots, it releases that radiation out into the lower atmosphere, and that's what really causes the atmosphere to warm up. It's heated from the bottom upward. And so when we look at that solar radiation coming from space, how much of it actually hits the surface of Earth and is actually responsible for warming up the surface and warming up the atmosphere? Only about 50% of that solar radiation actually makes it to the surface of Earth. Otherwise, it's being reflected or dispersed or absorbed, or something else is happening to it before it hits the surface of Earth. So only 50% of the radiation causes this warming of the atmosphere. And there's three different mechanisms for heating Earth's atmosphere. The very first one is the most important. It's called radiation. And this is something probably everyone who's watching this, you've probably seen radiation warming the lower atmosphere because you've probably been in a car and you're on a long stretch of road and you look way up ahead and you see those squiggly lines coming out of the road. That right there is infrared radiation. It's heat energy leaving the pavement and it's warming up the lower atmosphere. And this really is the most important way that the troposphere where we live is heated up. The next mechanism is conduction, and this one really is not very important. You're going to see why. Conduction is just the transfer of energy through molecular collision. So in our example, the picture, you see a pot of water boiling, and the bottom of the pot is receiving the most energy from the fire. And so those molecules on the bottom of the pot, they start to speed up, vibrating in place as they gain energy, and they bump to the slower molecules next to it, passing along that energy by a physical molecular connection, a bumping into, running into each other. And that energy is transferred the bottom of the pan, the side of the pan, all the way up to the handle. And that's why in some cases the handle of pots and pans as you're cooking can warm up. It's through conduction, the transfer of energy through molecular collision from the bottom of the pan, bouncing into each other all the way up to the handle. And if we apply this idea to Earth, we're really only talking about a very small layer of molecules that is almost in contact with surfaces that gain radiation. So it's really not a big deal. The second most important way we heat our atmosphere is through convection. And this is a word you've heard of before. You guys know about convection currents in the mantle. Yes, there's also convection currents in the atmosphere. So this is the rising of warm air. It spreads out and cools off as it rises, and then it sinks when it cools and gets more dense back down to the surface of Earth, where it heats back up, and this process just repeats. It's convection currents as you know it. And these convection currents are important for heating the upper layers of the troposphere. It's what causes heat to rise in the atmosphere at all. And it's just important to kind of think of rising air expanding, and that's what causes it to cool. And the opposite is also happening. When air subsides or sinks back down towards the surface, it's being compacted together, squeezed by air pressure, causing the air molecules to bump into each other more, which is friction, so it actually warms up as it subsides. Cools as it rises, warms as it sinks. And so how does all this heating of the atmosphere actually really make a difference to weather? And it's really tied to this idea of unequal heating and cooling of Earth's surface. If you look at a map, a big map or a small map, you can tell that there's different types of surfaces that cover Earth. There's water and there's land. That's the two we're going to focus on. And those two surfaces, water and land, they heat up and cool off at different rates. And think about this. Think about if you go to the beach in the afternoon on a hot day in August, and you park your car and you kick off your flippy flops and you start running across the sand. What does the temperature of the sand feel like? It's burning. It is like 1,000,000 degrees, plus or minus a couple, but it is super hot. And you tiptoe your way, you run through the hot sand until you get to the water, and you put your toes in the water. And how does that water feel relative to the temperature of the sand? very cold. And that's just because the land, the sand in this case, and the water heat up and cool off at different rates. If they heated up at the exact same rate, the water would be also 1,000,000 degrees and boiling, just like the temperature of the sand is extremely high. But they don't do that. And these differences in heating and cooling lead to potentially weather forming. And it's kind of important to note here the warmest part of the day. And some people tend to say noon when the sun is at the highest point, that's the warmest part of the day. And that's not exactly right. It's actually later in the afternoon, let's say 2, 3 o'clock. And if you remember how the atmosphere is heated up, it's heated from the surface of Earth upward. That makes a lot of sense. The surface of Earth is collecting this radiation from the sun all morning long and into the afternoon. And when the sun starts to go down past noon and it starts to decrease in the sky, the land that has accumulated all of this radiation, all of this energy, starts to release that energy into the atmosphere, and that causes the atmosphere to heat up. So the warmest part of the day is usually somewhere in the afternoon. An example of this unequal heating and cooling producing weather would be a land breeze or sea breeze. And these are different types of winds that are produced on a shoreline because of this difference in heating and cooling of the sand and the water. During the day, like we had just talked about, the sand is very hot and the water is very cool. And you have to think about, what does that cool water and hot sand do to the air right above it? The warm sand would heat up the air. Warm air rises. So we would create a low pressure area over the sand just simply because the sand is hot and makes that air move up. The cooler water would cool off the air, making it sink and subside, creating a high pressure. And if you remember our talk about wind always travels from an area of high pressure to an area of low pressure. So the wind in this case during the day would be blowing from the water, the sea, onto the land. We call that a sea breeze. Wind is always named for where it comes from. But what if we flip this? What if we flip it to nighttime? So now, for whatever reason, you and your friends decide to come back to the beach at midnight, maybe 2 a.m. I don't know what you're doing there. Probably nothing good. But let's say you're at the beach at night. And you do the same thing. You park your car, you kick off your flippy flops, and you start walking across the sand. What does the temperature of the sand feel like in the early morning hours? It's going to be very cold on your feet. And have you ever experienced this? If you tiptoe through that cold sand and you get to the water, what is the temperature of the water relative to the temperature of the sand? Yeah, it feels warm. It feels nice. And again, that's just because the surfaces of Earth don't heat up and cool off at the same rate. Sand can heat up very rapidly during the day, but it loses all of that heat at night and it cools off very quick. Water, on the other hand, does not have a big difference between daytime and nighttime temperatures. It doesn't heat up fast and it doesn't cool off fast. This property of land and water is called specific heat. Specific heat just really identifies how quickly or slowly something heats up and cools off. So water has a high specific heat. It takes a whole lot of energy over a long time to make water warm up. And once it has that energy, it holds it for a very long time and it cools off very slow. That's a high specific heat. Sand, on the other hand, has a very low specific heat, so it heats up rapidly and it cools off rapidly. So back to talking about this cold sand and warm water. Because the sand is cold, it cools off the air above the sand, making it sink and subside, creating high pressure. The warm water heats up the air above the warm water, causing it to rise. That makes a low pressure. And again, wind blows from high pressure to low pressure. So in this case, the wind would be traveling from the land to the ocean or the sea. And we call that a land breeze. And so this simple unequal heating and cooling of Earth's surfaces actually can produce what you might think of as weather, right? The direction and strength of the wind is something that's listed when you hear a weather report. And in some cases that are kind of rare, this unequal heating and cooling can actually produce clouds to form and also potentially precipitation. It's usually never severe like thunderstorms, but you could get cloud formation, maybe some light rain. That's going to wrap it up for today. If you have any questions, please make sure to let me know. And really make sure you're making some good diagrams and you're filling in your notes. Thanks. Bye.